So the agenda today, we're going to talk a bit about Ceph and SUSE Enterprise Storage, and David will be talking about that, and then I'll present some aspects of the PowerEdge server portfolio and talk about the range of servers and the options available for those servers. And then we'll switch back to David to talk about a reference architecture we did for deployment of Ceph using SES and PowerEdge servers. And also highlight some recommendations for when you're deploying PowerEdge and SES. And then I'll talk about a couple of case studies we've got for customers who've deployed SES on Dell servers, Dell PowerEdge servers. So with that, I'll hand it over to David.
Thanks, Gordon. So the first thing we want to do is talk a little about why Ceph. And really, there's several reasons. One of those is Ceph can really help you address multiple use cases within your environment. There's object storage, which is very cost effective and great for things like archiving, cold storage. Even today, you would look at use cases including data lakes, and even some HPC applications are starting to utilize object storage. There's also block storage. Block storage is a mix between the cost and performance optimized. You know, it's not super high IOPS like you would get out of the EMC portfolio, but it provides storage that is adequate for virtual machines that aren't running things like databases and things like that. So it's a key piece of that infrastructure. And then the file storage. Ceph includes Cephfs, which is a distributed file system that scales at the exabyte level. So it's great for also data lakes, backup, distributed computing, and then just massive network share environments where you have a lot of data that you need to deal with. So SUSE Enterprise Storage, being built on Ceph, is somewhat intelligent. It actually uses some algorithms that help it understand where data is placed and how to do that in a way that deals with fault domains. And this makes it really quite scalable and also quite resilient. So the way the data is distributed across the cluster, and we'll talk more about this in just a moment, protects you against node failure, device failure, and even up to data center failure in a multi-data center deployment. It helps you really reduce costs in your environment as well. The ability to use standard PowerEdge servers is a huge advantage in this case. It allows you to select the performance that you need out of your environment along with the density that makes sense. And it allows you to grow on the fly. When you slip in some new servers into your cluster, they could be the same generation or later, and it's going to automatically balance back across all of those nodes so that you're filling them up at the same rate. Just one of the features of SUSE Enterprise Storage. When we look further down in the stack, there's a lot of things like cache tiering, where you can have a flash tier sitting in front of a slower spinning tier. It's always thin provision. It allows you to select your data protection, whether it's using erasure coding or replication. Both of those, you can set the level that they're working at. You know, you can have 2 copies, 3 copies, 10 copies, depending on what you need for a particular data set. It's, you know, we've already talked about the fact that it provides block, file, and object. In those, we have the native protocols, but we also have protocols like iSCSI and NFS. So it's really this heterogeneous accessed storage. And it's really built, like we talked about, for scalability. And this includes being able to do things like online software updates. You update a node at a time and roll through the cluster without experiencing downtime. All great features. So Gordon, why don't you talk a little about the hardware portfolio?
Great, thanks, David. So at Dell, we do servers. There's a wide range in our portfolio of Intel-based servers with a selection of 1U, 2U, 4U form factors, 1 socket, 2 socket, 4 socket servers. So it really allows you to choose the environment that you want to deploy your applications on. We also have an AMD-based portfolio for 1U, 2U, and 1-socket, 2-socket rack servers. And then also, if modular servers are kind of a good target for your data center, there's some good options for those. All intelligently managed through the Open Manage and iDRAC architectures that are built into all Dell servers. To give you a view of some of the options, here we have a range of 1-socket servers, kind of good for kind of lower end application requirements in terms of performance. 2-socket tends to be kind of the sweet spot, and in particular for SES deployments, which we're talking about today, the R740 and the R640 and the R740XD are kind of in that sweet spot. The R640 is the 1U 2-socket server, good for some of the management nodes or control nodes, and the R740XD is a 2U 2-socket server, but you have a wide range of drives that you can put in there, either high capacity hard drives or SSDs or even NVMe, and so it gives you a lot of flexibility to configure the OSD nodes as you want to meet your requirements. And then we also have 4-socket servers if there's a real need for some high power requirements, and many of these also take GPUs if that's a requirement. You need some kind of acceleration for your application. We also have a wide selection of modular servers for the data center. So these tend to be chassis that can take storage sleds or compute sleds or networking modules. Similar types of capabilities to the rack equivalent. So the 840 compute sled would be 4-socket, similar to an R840, and the 740 would be a 2-socket. And we also have kind of other form factors which may help deploy applications in certain locations. The C series is a very well balanced, dense computing platform, really kind of optimized for high performance environments. Now, having this wide range of servers, obviously manageability becomes key, and so the Dell PowerEdge server portfolio has embedded server management, and it allows you to deploy those servers. You can inventory them, you can discover them, updating those servers, so maintaining BIOS and drivers is kind of a task that you want to make as simple as possible and automate as much as possible, including kind of the maintenance and monitoring. So getting alerts on health and performance, what's happening with the power on your servers, and then even if you need to replace parts. And Open Manage and iDRAC are the technologies that are built into Dell servers that allow you to kind of deploy, update, monitor, and maintain your server portfolio. So I'll hand it back to David.
Thanks, Gordon. So we want to step back and take a look now at the reference architecture work that we've done between SUSE and Dell. And the objective was to implement, test, and document really the process of deploying SUSE Enterprise Storage on Dell PowerEdge hardware. For the hardware, we started with the bare minimum. We wanted to show what you could do with a starter environment. And this is the smallest supported cluster really from the SUSE perspective in terms of the disk mechanisms, the OSD nodes. The white paper has a detailed bill of materials, so you could actually take that and implement it following the guide and have something that is up and running. For networking, we look to 25 gig networking, and the reason for that is really that in today's world, it doesn't make sense to build on anything slower than 25 gig. The price per port of 25 gig has come down significantly, and the performance and the signaling rate of 25 actually helps, especially if you're working in more latency sensitive environments, say where you're building perhaps all flash nodes. For the software, this was built on top of SUSE Enterprise Storage 5. 6 applies in the exact same way. And the hardware included being YES certified for the hardware, we YES certified the cluster, the storage cluster as well. That's an additional level of certification above the standard hardware certification level. So I want to take just a minute and make sure everyone's familiar with what Ceph is and how it works. We've talked about little pieces of it along the way, but this is really the holistic picture. You start at the bottom. What you have are a number of servers that we call OSD nodes or storage servers with a bunch of storage devices, disk mechanisms in them. Each device is assigned a daemon, a process on the Linux host. So a bunch of these together make up the entire body of storage, with each disk having intelligence associated with it. These are tracked by the monitor servers that you see on the right. These should always be an odd number because it does a majority wins voting algorithm in case there's disagreement between them for some reason. But they don't sit in the data path. They're just tracking who's up, who's down, who's in, who's out of the cluster. So all of these storage devices store objects. Everything that comes in, I don't care if you're writing in block, file, or object protocols, gets put into an object on the back end of things. Now this object store is called RAIDOS. That's the generic name for the entire object store. And on top of RAIDOS, we have the interfaces. These interfaces, like we've talked about, come in block, object, and file flavors. And with those, we have both the native clients, or what I like to call intelligent clients, and traditional clients. The difference really being that an intelligent client, the native, like RBD, RAIDOS block device, or CephFS, the client itself understands the pseudo-random algorithm called CRUSH that dictates where data is placed in the cluster. So the client talks to the monitors, gets the map of who's up, who's down, and all that. It calculates the data placement and talks directly to the daemons for each storage device. What this means is you have extreme levels of scalability because you're not going through a bottleneck gateway. Now, when we look at the traditional protocols like iSCSI, NFS, and Samba, you have one or more gateways that you are putting all of the traffic through. If you look at iSCSI in particular, in that world, we're used to talking about fan-in ratios. And there's a particular, bunches of numbers that you usually don't want to go past. This may be 64, 128, or 1024, whatever the number is. Those are there because you don't want to overload that single choke point. And when you talk about using multipathing, there are limits to what makes sense for the MPIO stack to handle on most clients as well, really enforcing that choke point. So consider a very large cluster where you have, say, 500 nodes of 60 drives each, right? Now we're talking 30,000 devices, right? Yeah, 30,000 devices in the cluster. And if you are talking directly to each one of those devices from every client, if you have a large number of clients, you're able to get a lot more aggregate throughput than you would going through a gateway protocol. And that's why we always encourage use of that native protocol over the gateway ones if possible. Now, when we get to object storage, very few people use the native protocol, which itself is called RAIDOS. There are some applications available, like C-File in the market, that allow you to make use of that. But the most common thing we see is S3. That's obviously the standard that Amazon created and is in use by most applications today that want to write to object storage. That scales horizontally as well. You just keep adding object gateways and have some sort of load balancing mechanism in front of it, whether it's load balancing switches or whether the application itself is aware of all of the object gateways and handles load balancing within the client. So both of those are completely valid options depending on what the application is doing, and it scales quite well. So in the lab, like we talked about, we have a full bill of materials, but in short, we had 4 R740XDs, a couple of Dell switches, and then we used PowerEdge R640s for the monitor nodes, the client nodes that we did testing from, and what we call the solution admin host. And this is a host that handles things like DNS, a mirror for the software repositories, things like that. And that's, again, all outlined in the document. You can see the network connections. If you look at the 740XDs, you see the blue connections on those only connect to one switch. This is a simplified diagram. In reality, the way we would deploy this is have a MLAG between the two switches, one port from the NICs to each server or to each switch, so that you're able to survive, a cable failure, switch failure, NIC failure, that kind of thing. But it's a pretty simple architecture, pretty robust in the way that it can be implemented. So from a design best practices point of view, and you see some of these reflected in this, we have dual top of rack switches like we just talked about. We really don't want to have failure of a particular component bringing down significant amounts of the infrastructure. That's just always a good practice, not just for storage. When we talk about really scaling large, say we go to that 500 node cluster, for example, that's where we start having to think about the network infrastructure and what that looks like. And the infrastructures vary by size, but if you're building a truly giant implementation, you probably want to look at some kind of spine and leaf type layout to your network. Mesh probably doesn't work so well at that scale, but in a small cluster, mesh may work fine. So make sure that you're matching up the network topology to the size that the cluster is expected to grow to. One thing that I try to get people to do is think about your IP allocation early. Don't limit yourself necessarily with Class C of address space if you're going to go over that at some point in a 5-year lifespan of a cluster. Re-IPing things is never fun. And really do yourself a favor. Try not to route storage protocols. Routing, S3 traffic is fine. But once you get to things like the block protocols, every hop you put in it is very important. Going down a little more through these, there's a bunch of things on here. I do like to talk about using LACP to bond connections together. We talked about doing an MLAG. On top of that, I typically do divide the traffic up using VLANs so that I can combine all the ports into one logical connection and break out the VLANs for segmentation of traffic beyond that. And then think about your storage. What really makes sense, right? You have a lot of choices. You have SATA and SAS in both hard drives and in solid state. And then you have things like NVMe. Pick the one that best suits your use case. Don't use hard drives if you're trying to deal with something that may have some level of latency sensitivity to it. But also NVMe, probably not the best choice for something that is really more about storage density. You do have a choice when it comes to your spinning media about how you should make it appear to the system. I always recommend that you use a battery-backed caching RAID controller loaded up with cache and set each device to be its own RAID 0. And the reason for that is that having the battery-backed cache allows you to enable write caching against the devices, and it helps level out the peaks. When you have a real bursty peak of amount of write come in, it can keep the latency from spiking heavily. And then offload RocksDB. This is where the metadata is stored. Offload that in the write-ahead log to NVMe devices. With an NVMe device, you can get ratios around 12:1. And what that really does is it speeds up all the metadata operations. And if you have a cluster with a lot of data going into it, especially if you're looking at things like Cephfs, you really want to make sure you're offloading that work onto a faster medium. So back to you, Gordon.
Great, thanks, David, for that. So yeah, I'd just like to highlight a couple of customer case studies. Details of these can be found on SUSE.com. The first one is FACT, an IT provider. They're a one-stop shop for hardware and software solutions and infrastructure hosting. And so one of their customers, telco, had a voice over IP application fairly high usage in terms of payments per month, and generating a lot of data every month. And so they went with a SES deployment on Dell PowerEdge R730 XD rack servers, and deployed a mix of capacity hard drives and SSDs to kind of accommodate the application requirements, and really kind of achieved a lot of efficiency and flexibility. They were looking for expandability being fairly easy, as they knew that the amount of data they were going to consume every month increased. One of the features was the management tools available on SES. It was certainly significantly better than standard Ceph, and that was kind of one of the attractions. And also the OpenStack integration and the support for iSCSI were kind of key features that also helped sway them to kind of go with SES as their storage solution, and subsequently have deployed additional clusters. And then the next case study is Swinburne University in Australia. They are a fairly large Dell customer. They've got a supercomputer based on Dell servers, but they were actually looking for an enterprise backup and recovery solution, and decided to go again with SES and Dell PowerEdge servers. One of the key requirements for them was high availability, and so they wanted to be able to do continuous replication between primary and backup data centers, and we're able to achieve that. High performance and scalability were kind of key components, as well as lower cost. I mean, obviously these are very kind of cost-effective deployments for the sheer capacity that we're deploying here, so yeah, so they've kind of expanded that since the original deployment. So hopefully we've given you a flavor for how you can deploy SES on Dell servers. There's a good range of servers to choose from to help meet your business requirements. The Dell servers make a great platform for Ceph, and in particular SES. And SES has already been deployed in customer environments, and as I say, you can go and read about those in a little bit more detail on SUSE.com. And you know, we would love to have you on board as customers and see you deploy your SES storage on Dell servers in the future. And with that, we'd like to thank you for listening to this SUSECON presentation.